So in these next couple of videos, I'm going to be doing a full review of torque and rotation. Um, it's going to be a couple parts, I think about 5, because it's just a lot of information, and it's going to be about 10-minute long videos for each topic. Um, just makes it easier for you guys to take in the information, and let's say for torque, you know what you're doing, but for rotation, you just don't have it. It'll be split into parts so that you can really watch what you need to watch. So in the description, I'm gonna link a PDF of all the information here with all the practice questions that I'm gonna do, so that you guys will be able to follow along, and you'll be able to watch, and it'll be helpful. So let me know what you guys think about these videos. I still don't know if I want to do short form content or these longer videos, so feedback is really helpful. So just let me know if you guys want to see more videos like this, or if you guys think that it would be helpful if I just stick to single question type videos. So hopefully you guys enjoy. Make sure to like and comment if you did enjoy, and yeah, hopefully this helps. So first, let's start off by talking about what is torque. Well, torque, which is going to be represented by the tau, it's going to look something like that, is going to be an applied force that makes an object rotate. So torque, T, is going to equal F r sine theta. So torque is going to be a force. So let's say we take a rod, okay? And we have this rod hinged on something. And we're going to apply a force here, okay? We're going to apply a force at the very end, okay? Our radius is going to be the distance from our hinge where we're turning. So this is going to be r. And let's say we apply a force of 10 newtons. So we're going to be applying a 10 Newton force down. So 10 newtons down. And our theta is going to be whatever our force is relative to, the line of our radius. So that's obviously going to be 90 degrees. So then our torque would be 10 and then r sine 90, right? So sine of 90 is just 1, so it would just be 10r. So something we should understand is that if theta is not given, like we did here, we're going to assume that it's 90. So obviously, if the theta is 0, then let's say we apply a force like this, right? We have a rod and we just apply a force like that. Our theta is 0, and so we have no torque because sine of 0 is 0. And so similarly, the more our theta is, the higher our theta is. So let's say we have, this is our theta. The closer to 90 that our theta is, the more torque we will apply, the greater the magnitude of the torque we will apply. So when you're, trying to tighten a nail or use a wrench, that's why you're going to use that wrench at a 90-degree angle from the nail. You're going to hold it, you're going to turn it at about 90 degrees from the nail because it'll be easier. So another thing that we should notice, or note, I should say, is let's say this is a rod and we're going to apply a torque, okay? We're going to apply one torque in this direction, so I'll just say T, and one in this direction, okay? So with torque, counterclockwise is positive. So this torque is going to be positive, so all right, positive, and clockwise is going to be negative. So this torque is going to be negative. So similarly to rotational motion, or circular motion, I should say, counterclockwise is going to be positive, clockwise is going to be negative. So let's talk about equilibrium. So we know from dynamics that translational equilibrium, we call it, is when the sum of the forces of an object equals 0. So if we have an object here and there is a 10 Newton force down, and then there's a 10 Newton force up, our object is in equilibrium, which means it has no acceleration. And this is why normal force is a thing, right? We have an object with a force of gravity, but it's not moving. The reason why is because we have our normal force. So what we have to understand is that for an object to be in equilibrium while rotating, is it needs to have translational equilibrium and rotational equilibrium. So we need the forces, the net force, to be 0, but we need to add now that we need our torque to equal 0. So both things need to be true. So let's give an example of something that might be in translational equilibrium but not rotational equilibrium. So if we have an object here that has 10 newtons up, 10 newton force up, 10 newtons up, and let's say it's going to be hinged about this, about here. So we have a 10 newton force up, and let's say that this is 2 meters long. Okay, so this is going to be 2 meters long. And now we have a force down of 10 newtons. You would say that this is in translational equilibrium because F up plus F down is 10 minus 10, which is 0. But this is not in rotational equilibrium. And this is because if we do our force times our radius times sine theta, even though that's going to be 90 degrees, so we could just cross that out because it'll be 1. For our force times our radius here, it's going to be positive 10, right? 10 times 1, which is the radius. And then here, it's going to be 10 times 2. So minus 10 times 2 is 20. We're going to be at negative 10. So our torque does not equal 0. So what we need to understand is that when we're trying to get an object in rotational equilibrium, we need to be mindful about where we place that second force or that third force or whatever the force is, because we can't just place it anywhere. We need to know, okay, where is it hinged? What is it rotating about? And how much force are we going to put? You know, maybe you'll have to put, 2 different forces in 2 different areas to, balance it. So let's take a look at some questions. So if you will just give me a moment. So question number 1, and during this video, most of these questions are going to be MIT conceptual questions. Some of them are going to be, numbers, but on the AP exam, most of the questions are going to be conceptual, not really using numbers. So that's why there aren't going to be a lot of numbers in this video. So in this question, we're asked for the wheel and axle system shown above, which of the following expresses the condition required for the system to be in static equilibrium. So again, we remember that for a system that has rotational forces, we need to be in translational equilibrium and rotational equilibrium. So what needs to happen is that our F of G and our F of G from here need to be equal in magnitude, but also we see here that these forces, or these masses I should say, are a different radius from the center of this, this wheel. So we see here that this mass 1, is attached at a radius A from the center, and this mass 2, is attached at radius B from the center. So if we look here, we can say that this mass is going to cause the wheel to rotate this way, right? And then we can say that this mass is going to cause the wheel to rotate that way. And so obviously here they're in different directions. So we know that the magnitude of these forces need to add up to 0, right? So they need to be the same. So we know that the torque needs to equal 0, which means that FR for mass 1 needs to equal FR for mass 2. So we know that for mass 2, we can say that the forces for both of them, I should say, equals mg, right? So we know for mass 1 we have m1 times g times a, right, our radius of a, and that needs to equal m2, the second mass, times the gravity for that mass, times the radius b. So then we look here and we can cross out the g's, right? Not important because they're the same. So we can say m1a has to equal m2b. So our answer is going to be B. All right, so taking a look at this next question, we see a system of two wheels fixed to each other is free to rotate about a frictionless axis through the common center of the wheel and perpendicular to the page. Four forces are exerted tangentially to the rims of the wheel as shown above. The magnitude of the net torque on the system about the axis is what? So first what we should do here is we should look at where these forces are going. So we take a look, we say that this force, the first one, is going to make the wheel turn this way, right? This force is going to make the wheel turn that way. This force is also going to make the wheel turn that way. And then this force finally is going to make the wheel turn the other way. So these three forces on the bottom are all going this way. They're all going counterclockwise. And then this one is going clockwise, the 2F. So what we can say here is the net torque on the system is equal to, we can say, the torque counterclockwise plus the torque clockwise. So we can say here that for the counterclockwise torque, we're going to have for our first torque, we have a force of just F and a radius of 2R. So F times 2R, that's an R, plus for our second one, we have a force of just F and a radius of 3R, so F3R. And then finally, we have another force of F with a radius of 3R, so plus F3R. And then here, we're going to have plus, for our clockwise, we're going to have negative, because again, remember that clockwise is negative torque. So we're going to have negative 2F times a radius of 3R. So we put these all together, we're going to get 2 plus 6, so 8FR. And then minus here, we're going to get 6FR. So in total, we get 2FR. So our answer is going to be B. All right, so let's take a look at this last question. So we're given a rod of negligible mass is pivoted at a point that is off center so that the length L1 is different from L2. The figure above shows two cases in which masses are suspended from the end of the rod. In each case, an unknown mass of M is balanced by unknown mass M1 or M2 so that the rod remains horizontal, which is the value of M. So what we know here is that since the rod remains horizontal, the torque on this side of the rod is equal to the torque on this side of the rod. So similar to how it's going to be here. So what that means is that our FR on the left sides is equal to our FR on the right sides, right? So we can say that M times L1, and I'm looking at the first rod, equals M1 times L2. And then we can also say that M2 L1 for the second rod equals ML2. So we want to get M by itself, right? We want M. How can we do that? Well, we need to either get rid of L2 in this equation or L1 in this equation. So I'll just get rid of the L1 in this equation. Either way, you're going to get the same answer. But so we need to substitute L1. So here we can say L1 equals ML2 over M2, right? So here we would say M times ML2 over M2 equals M1L2. So we'll say M squared L2 over M2 equals M1L2. So these L2s will cancel, and then we multiply an M2 over. We say M squared equals M1, M2. We square root both sides, and we get that M equals the square root of M1 times M2. So our answer is going to be D.